When packed in air, food is susceptible to three main spoilage mechanisms: simple oxidation, bacterial growth, and mold growth. However, all of these can be suppressed or reduced by packaging the food in the appropriate modified atmosphere. In this video, we're going to learn about a modern method of food packaging called Modified Atmosphere Packaging, or simply MAP. First, we'll talk about the purpose of this method, and then we'll take a deeper look at its requirements. Finally, we'll consider some examples in our further understanding of MAP. So, to figure out what MAP exactly is, let's start with the basic concepts. Simply put, in this method, we modify the atmosphere surrounding a food product by removing the air inside of its package and then adding the gases that are safe for both food and customers' health to control the biochemical, enzymatic, and microbial actions without temperature or chemical treatments. In most cases, MAP is aimed at eliminating or reducing oxygen inside the packaging and replacing it with a mixture of carbon dioxide and nitrogen. Of course, in special cases, such as packing red meat and fresh produce, the opposite is correct. We do not eliminate the oxygen, but instead increase its concentration to prevent anaerobic growth. MAP therefore normally requires a mixture of at least two gases, and the optimum proportions vary from product to product. So what are these gases we use for MAP? All of these come from the air. The first one is oxygen. Oxygen, or O2, as we all know, is highly reactive, and most of the common spoilage bacteria, fungi, and chemical and biological reactions require oxygen to live and grow. Therefore, to increase the shelf life of most foods, the pack atmosphere should contain a low concentration of oxygen. The next one is carbon dioxide, or CO2. Carbon dioxide is both water and lipid soluble, and although it's not a bactericide or fungicide, carbon dioxide has bacteriostatic and fungostatic properties. The overall effect on microorganisms is an extension of the lag phase of growth and a decrease in the growth rate during the logarithmic growth phase. The last is nitrogen, or N2. Nitrogen is a relatively unreactive gas with no odor, taste, or color. Using carbon dioxide alone can lead to a volume decrease due to carbon dioxide going into solution. So for many food products, CO2 requires a second gas to balance this volume decrease, and this gas is nitrogen. The low solubility of nitrogen in foods can be used to prevent pack collapse by including enough of that in the gas mixture. Okay, as it was mentioned, we're not going to mix these gases in the same way for all kinds of foods. Depending on the type of food products and specific causes of their spoilage or quality deterioration, the gas mixture would be different. For example, mechanisms that limit the shelf life of raw red meats are microbial growth and oxidation of the red myoglobin pigment and convert it to oxidized brown metamyoglobin. For this reason, high concentrations of oxygen are necessary in order to maintain the desirable red color for a longer period of time. With the right mixtures, the practical shelf life of consumer-packed meat can be extended from 2 to 4 days to 5 to 8 days at 4 degrees Celsius. Also, carbon dioxide has a strong inhibiting effect on the growth of bacteria, of which the Pseudomonas presents the greatest problem for fresh meat. As another example, let's consider dry foods and snacks, like peanuts, potato chips, and baby milk powder. These foods contain unsaturated fats that make them sensitive to oxidation and rancidity when oxygen is around. So the oxygen amount must be reduced to under 1.5%, and the rest of the air inside of the package must be replaced with nitrogen. In the packaging of some other types of foods, such as cheese, the mixture is completely different. In this case, carbon dioxide is used first and foremost. The carbon dioxide level in hard cheese packages is up to 100%, and for soft cheeses, the level is usually restricted to 20 to 40%. The reason for this is to prevent the package from collapsing under atmospheric pressure as the carbon dioxide dissolves into the water content. With ready meals and catered foods, customers expect healthiness and high quality with long shelf life, without chemical additives, with minimal perpetration. In order to meet these demands, atmosphere control combined with the correct temperature is the best solution. Low oxygen level with a high level of carbon dioxide will promote such product shelf life. There are lots of other food categories requiring specific MAP gas mixtures. Fresh produces are one of the most important types, and we'll show you in another video a new exciting method for keeping them fresh during transport. Now that we've got familiar with the gas mixture concepts, let's see how we select the best packaging material, as it's essential to maintain the quality and safety of MAP foods. There are 6 main characteristics to consider when selecting packaging material for modified atmosphere-packed foods. These characteristics are resistance to puncture, sealing reliability, anti-fogging properties, carbon dioxide impermeability, oxygen impermeability, and low water transmission rate. All in all, there are lots of benefits of using MAP: increased shelf life, little or no need for chemical preservatives, improved presentation, clear view, reduction in production and storage costs are some of its advantages.